This is ECE588 project presentation. The title, Robot Vision Object Detection Algorithm for Game Application, Real-Time Shape Following for Collisions with Animated Objects. The presentation date is Wednesday, August 5th, 2015 by TimothyKushnier and DennisBreton at the University of Michigan Dearborn Electrical and Computer Engineering Department. The course instructor is Professor Larry C. The PowerPoint presentation is available on YouTube at the following URL, as well as a video demonstration. Introduction. Robot vision is possible due to execution of computer programs that react to and interact with an entity other than itself. This project demonstrates the performance of object, in this case a blob detection, real-time object tracking, real-time object interaction with dynamic computer animations. Please view the video demonstration at this time. To view the demonstration, you can double-click the URL below or paste the URL in a web browser, and after viewing the demonstration, please return to the slide presentation. So what makes this robot vision? The program could be deployed in a machine unit with mobility, in other words, a robot. The computer program responds and reacts to real-time input. Once coded and executed, the computer program does not rely on human intervention or training or any type of machine learning. The inputs and outcomes will never be statistically identical from one session to another. Therefore, the machine responds dynamically to situations it has never encountered. Game application. Rudimentary implementation of methods that are likely or possibly employed in existing commercial game consoles. The basic premise of this game is similar to classic Atari Space Invaders. Instead of a wired mechanical or joystick feedback into a game field environment such as a console or CRT monitor, the stimulus is captured in real time via an inexpensive webcam. The actions of the active participant, or the one who controls the light, quote unquote, to be detected by the computer algorithm, are additionally tracked throughout its series of movements. When the external stimulus scores a collision or a hit with the animated graphical object, which in this case are descending balloons, the animated descent rate is increased for the next descent. Development tool environment. For this project, we worked predominantly with MathWorks MATLAB, in this case version 2015A. Specifically required were the MATLAB image processing toolbox as well as the computer vision system toolbox. A webcam, which I mentioned in this case is a very inexpensive webcam, personal computer running Windows 7, and an Apple iPhone, which was used to record the demonstration. The development work performed. There are two main software components: the main part of the program, in which case the code is attached here at Appendix 1, and a determined centroid function, and the code of this is attached in Appendix 2, and we'll discuss both of these components in the next several slides. The main program code. The purpose of the main program code is that it creates the game animation of descending balloons and the finish line. It reads in the camera image, and in the main loop it updates the balloon position in relation to the finish line. It determines the descent rate of the balloons, again based on the hit rate or number of hits of the previous iterations of the falling balloons, and it calls a function that determines the blob center and determines the collisions or hits. The determined centroid function is called from the main loop and is passed the camera image as its input. It converts the input image from RGB to HSV format and extracts, in this case, the saturation content. It performs image thresholding, conversion to black and white image, and combines the connected components as the brightest, which are determined as the brightest pixels to detect the blob image. It finds the centroid, which is the center of the blob, and encircles the blob shape. It returns the center point coordinates back to the main loop. Getting started. For detecting the blob-shaped object and determining its center coordinates, different filtering methods on sample images were attempted. As well, some of the following steps were taken. We displayed the filter image to determine best outputs. We viewed RGB and HSV color spaces. In our case, saturation from the HSV gave us the most information. We took the best output and filtered further. Further work included a pipeline type of approach, which we took to further process the input image, mainly by trial and error of many different methods until an adequate output was achieved, the game could be reasonably played. From there, we finally further tested threshold values and other image conversion techniques. We played with grayscale, we played further with HSV and black and white until the optimum output was achieved. Design decisions. So I think one of the most difficult decisions was in selecting a topic and planning the game design. So some of the design considerations, of course, are the game board composition and what approach to take for the vision coding of the algorithm. Blob detection, a decision was required whether to work in positive or negative space. The best use of centroid finding feature to meet our requirement, and mainly deciding what to do and working through a number of possibilities until finding the means to implement exactly what we wanted. What worked for us? Centroids, definitely centroids, for finding the geometric approximation of the center of the blob and for detecting and encircling the connected content of the brightest blob. Saturation operator worked as well as brightness. Again, it was just a matter of deciding whether we want to work in a positive or negative space. The pipeline approach, again, was a useful idiom, and mirror imaging of the camera input was critical to being able to play the game in the way that we intended it to be played. What didn't work? Lighting was a very big problem for us. So the flashlight as a source for object to be detected was highly inconsistent. Part of the reasons being that the algorithm performed poorly at distinguishing between the projected light beam and the bulb as a source. So because the bulb was brighter, it was often detected as the blob. When the source or the bulb was moved out of the lens image area, which was a small range and it was difficult to manually stay within when moving the flashlight by hand or playing the game basically at near range, the beam projection then became the brightest or largest blob. So there was a competition between the bulb source and the light beam, depending on where in the camera range either of them fell. Second, performing a resize of the captured camera image prior to running it through the algorithm. And this was intended to address the issue that I just spoke of in the first point. We could not get this approach to work as intended for resizing or narrowing the captured light source, and this was attempted again to control the resolution and increase consistency in detecting the light blob. And third, certain lighting environments impacted the results, so ultimately we chose to control the lighting environment by darkening the room, but not completely dark, and manipulating the object to be detected. Instead of using the flashlight as a source, what was done then was we covered the light source with a white piece of paper, basically a white circle, and allowed the algorithm to detect that as opposed to detecting light. And this definitely improved the situation. In point number one. And additionally, by surrounding it with a black background, in this case black construction paper. So at this point we were not detecting a flashlight of any kind. We were basically using the flashlight as a handle to move around the basically black background with centered with a white circle, and this became our new so-called light source. Obstacles overcome, mainly again lighting and light source decisions. changing and reworking algorithms, attempting to narrow the light detection to make it more controllable. This was done primarily based on some of the homework assignments that used resizing functions and also resizing in a pyramid-like approach. Neither of these approaches gave us much success, and I suspect that it had to do with the way that we tried to call those functions and pass arguments between the functions. And finally, the decision to rein in and control the light source and the lighting environment in a better way was really, I think, one of the main obstacles that we overcame. And once we made this decision, the game played much easier and was indeed much more enjoyable. What we learned: many environmental variables to consider. Shapes and lighting are big ones. Lighting has a critically high impact. We were fortunate to have good MATLAB documentation and lots of online information for what we were trying to do. A lot of practice and trial and error can be a good learning tool, and stepping through the code line by line and looking at images output at every possible step that produced an image was invaluable for learning and understanding, in addition to monitoring the MATLAB workspace variables. So these are things that developmental procedures that we found very, very helpful. What we could have done better: the computer program responds to a single live camera input image capture, and what we would have liked to have done was to have had multiple cameras and have two real live inputs that meet up in the virtual computer world. So perhaps one is the light source and perhaps another would be real balloons, and somehow have these merge in a virtual environment. The Huff circle detection procedure would have been useful to have been implemented on this project, so that the detection algorithm would maintain consistency when the blob area that was being detected, and of course which was referring to the white light, when it went out of the range of the camera image area. Again, we mitigated this issue by changing the light source and the structure of the light source. It would have been better, I think, to deal with this in the code environment, and additionally to understand the update rate of the camera input and understand the processing speed of the algorithm. This may have helped our issue. Understanding these timings may have helped our issue with kind of the algorithm battling between the bulb light source and the light beam to determine which should be the blob to be detected. So references here, again, MathWorks help documentation is as always pretty excellent, with a lot of excellent examples. We were able to expand on those examples, and through a lot of trial and error we ultimately had everything that we wanted or needed at our disposal. And there are a few other references here regarding computer vision and more MATLAB and Simulink examples.